Okay, now I don't want to give you guys too much confidence. Been there before when we had Unit 2. I told you guys, hey, we're going to start off this marking period. It's going to be an easy test. And I thought you guys were all going to get A's and then didn't quite go as planned. So, when your teacher is telling you everything you need to know for a test, like I am about to do right now, I would pay attention closely. And I would ask questions if I don't understand something. So, this test, though, a large, very large portion of it is stuff that we've been working on for quite a while, even back into Unit 2 stuff. Talking about the phases, okay? In this unit, really what we're doing is we're taking what we know about the phases, solid, liquid, and gas, and we're just really trying to focus more on the energy involved, because that's what this unit's about. But we know, like particle diagrams, we know solids are really close together, and they're just vibrating back and forth, okay? And we know in a liquid they're a little more spread out, and since they are moving past each other, we can draw arrows on them. Not real big ones, though, typically. And then for gases, we're going to have them really spread out with big arrows because they are going fastest. Okay? Now, the other thing we need to think about with, did you just say OMG about fastest? Yes, look it up. Bet you $100.
I'm the fastest person in the room.
Look it up. All right. Right. Okay, so focus here. Let's get back to this. My fault. So we got to think the energy involved with like what we talk about phase changes, phase energy. One of the big things we learned is that the temperature does not change during a phase change. Okay, so all right, look, guys, I only have a limited amount of time here. Let's pay attention. Okay, so listen. If we think about attractions between particles, like shaking hands or something, or holding hands, it's easier to do if you're closer together. So where the particles are closest together are going to be our strongest attractions. Okay, and then as we go through the phases, the spacing, as they get more spread out, the attractions are going to get weaker as we go to the right. So liquid has weaker attractions than a solid, and a gas has the weakest attractions. Weakest. Yes. All right. We already know, I mean, it's nothing new for me to say that what arrangement of particles in solid, liquid, gas. It's nothing new for me to talk about the speed of the particles. These would have the most energy, you know that. And typically we see that these have the highest temperature. Okay? Make sense? But understanding the phase energy, the energy that's needed to overcome these attractions, is a big deal. All right? And that's why when we did the heating curve, we saw those flat spots. So we should know those flat spots. Cash on your phone. We should know those flat spots are phase changes. So over on the y-axis, what we have is temperature. That's what this is. Whatever units, doesn't really matter. And this is time. And over time, we are adding energy. Okay? So what phase are we going to have at the lowest temperature? Okay, solid. They're the lowest temperature because the particles are moving slowest. They're just vibrating back and forth. So particles moving really slow. Now as we add energy to them, they're going to vibrate back and forth a little faster. Vibrate faster, moving faster until we get to this point here. Now at this point here, the temperature is not going to change. That's because all the energy that's going in is for a phase change. All the energy going in is changing it from solid to liquid, which we call what? Melting, okay? So we know that this flat spot, the lower temperature flat spot, is melting. So I could ask you to label that. I could even ask you for the number. I could say, what's the melting point of this substance? And you should be able to tell me, oh, it's 30 degrees, 28, whatever. Okay, so everything gets melted, and then we've got a what? Liquid. And then as we add energy, we will see those particles in the liquid move faster and faster and faster, 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 till we get to here. Boiling. So this is the boiling point. We could also say vaporization. All right. So then we would say the boiling point is 80, whatever. Okay, so it boils. All the energy that's being added right here is changing it from a liquid to a gas. If we contain the gas and took the temperature of it, we would see the temperature of the gas continue to increase. I'll do blue to show the cooling curve going right to left instead of left to right. If I take a gas and I cool it, the particles are going to move slower and slower and slower and come closer together until we start forming a liquid. Gas forming a liquid is called condensation. So the condensation point and the boiling point are the same thing. It's just different directions. This is going from gas to liquid. Once it all turns into liquid, we can cool the liquid, cooler, 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 and then it freezes. Okay? And it turns into a solid. That's right. So that's a freezing point. So freezing and melting point are the same number. In this case, for this substance, 30 degrees, just different directions. When it all freezes, we get a solid, and then we can make the solid colder. So you should be able to label all those parts. Okay? You should remember the types of energy. So when the temperature is changing, like here, that is kinetic energy, right? You got to remember that temperature is equivalent to speed of the particles, which is really the kinetic energy, which they might say average kinetic energy. We're taking the average of all the particles' speed, okay? But in these flat spots, the kinetic energy is not changing. So if the temperature is not changing, the kinetic energy is not changing, the speed is not changing. What is changing is that phase energy that we started talking about with those LOL charts. And those LOL charts, that's the last thing that we did. That's the last thing you need to know for this test. So on those LOL charts, that was bad. That was bad. We have two types of energy we're looking at, thermal energy and phase energy. So let's say I have a liquid, water, let's say, and it's in a pan, and I'm going to boil it. So we got to understand that for thermal energy, which is really like the temperature, the motion, the kinetic energy, let's say it's at room temperature. So I'll do 2 blocks. You got to memorize the standards for doing these. Like for thermal energy, one block is cold, 2 is room temperature, which would be like 17 to 20 degrees Celsius, somewhere around there. 3 would be warmer, and 4 would be hot. For the phase energy, what we do is we do 1 block is solid, 2 blocks for liquid, and 4 blocks for gas. So first we got to identify what is our system, what is our focus, what are we looking at? And in this case, we want to pay attention to the water. Is the water gaining energy, losing energy? What is it doing? Okay. So at the beginning, what is it? What phase? Okay. Well, I put room temperature for thermal energy, but what is the phase? Liquid, so I put 2 blocks, right? Let's say I'm just heating the water. I'm not even going to worry about boiling it. I'm just going to heat it. All right? So if I heat it, but it's still liquid, then that means my final phase energy is still going to be 2 blocks. But now what about the thermal energy? It could be 3. I didn't say how much energy I'm added. It could be 4. So like I said, you might have a slightly different number of blocks compared to another student. It doesn't mean you're wrong or they're wrong. You can both be right. So that would be like heating it. Maybe I heat it to hot. I don't know. Um, so what we do next after we have our blocks is count the number of blocks on each side. Okay? So I have 4 blocks on the left. I have 6 on the right. So what is the difference? 2. So yeah, we gained 2 blocks of energy, right? So 2 blocks, arrow pointing them in. It's heat energy, so we put Q. And we call it endothermic because the energy is going in. So N in, that's what that means. Huh? I doubt you will. All right, but you need to know how to do those charts. On that worksheet we did, we also explained particle motion. But what would we say for particle motion in here? Is the phase changing? It's not. So it's still liquid. So the particle spacing, there could be some differences. The fact that they're moving faster would mean that the particles could have a little more spacing, but it's not like they're spread out as much as a gas. What about the speed of the particles? Well, what if we're just heating it? Is the speed of the particles increasing? Yes, okay. As we add energy, the particles are going to move faster. That means faster speed. That means higher kinetic energy. That means higher temperature. Okay? So temperature changes as we add energy, but not during a phase change. If I took the same substance and I just boiled it, so let's say that was the double LOL chart you did, I would just add a couple blocks to the phase energy over here. But during the phase change, the temperature doesn't change. And that's pretty much all there is to know for tomorrow. Okay? Take a look at those papers you got back. And it should be good to go.